Okay, I think it worked so far.
Good. It takes time people to join, always the last minute.
Yeah. Yeah, I can see the stream. Um, okay.
Welcome, everyone. We're going to start in just 1 minute.
All right, I'm going to start recording.
Sure. Hey, hello, everyone. Welcome to the 118th Online Spintronics Seminar. And also Happy Lunar New Year if you're celebrating it. It's my great pleasure to introduce our speaker today. Dr. Larrauri is Assistant Professor of Mechanics and Materials Engineering at the University of Nebraska-Lincoln. He's also a focused research group leader on quantum sensing and technologies of the 2021 NSF $20 million EPSCoR Center on Emergent Quantum Materials and Technologies. Dr. Larroy earned his PhD in physics from University of Strasbourg, France, under the supervision of Dr. Jean-Yves Bigot, where he developed a time-resolved magneto-optical microscope to study the magnetization dynamics of magnetic nanoparticles excited with femtosecond laser pulses. Soon after his graduation, he received a Marie Curie Fellowship from the European Research Training Network to carry a postdoctoral position at the University of Kaiserslautern in the group of Professor Burkhard Hillebrands. He used the Brillouin light scattering microscopy to study spin current-induced spin wave emission in spin-torque nanooscillators. After that, Dr. Larroy joined City College of New York as a research associate to work on a methodology to use the spin of NV center in diamond as a probe for high-resolution magnetic and temperature imaging at a nanoscale. In 2016, he joined the University of New Mexico Center for High Technology Materials as a research assistant professor. And in August 2019, Dr. Larroy joined UNL as a tenure track assistant professor. And his current primary research focuses on developing new quantum materials based on color centers in diamond and defects in van der Waals materials for applications in quantum sensing and nanoscale magnetometry. So without further ado, Dr. Larroy, please take it from here.
Okay, thank you, Sin, Khalil, for the invitation. I'm looking to present our recent work on imaging room temperature scandium ingredient, DMI, engineered cobalt platinum single layer films. So for my talk today, okay. So I will, the outline of my talk, I will start with a short introduction about, introduce exactly why scandium and why Jellinsky-Mariana interaction is correlated with scandium. So I show this number of papers per year from 2005 until now, until 2021, where there is direct correlation between the number of DMI articles and also there's like exponential growth of the number of scandium articles. That gives the importance of these spin textures for different kinds of applications. So then I will talk about how we can engineer DMI by engineering the composition of ferromagnetic layer in cobalt platinum baseball single layer films. Then I will talk about using topological Hall effect, MFM imaging of isolated scandium in these graded cobalt platinum single layer films. And then since we'll spend some time to use ND microscopy in particular, I will talk about the basics of ND microscopy, how we use that technique in our lab to study different solid state phenomena. And then I will show you we can combine NV microscopy with micromagnetic simulation to reconstruct block skyrmions, and as well observe or image like isolated skyrmions or skyrmion pairs that we made described by different kind of interactions. And then I will summarize my talk and talk about the ongoing projects related to these materials. So I'll just give some introduction, in particular for people who are not familiar with this topic. Usually, magnetic skyrmion are kind of similar to vortices, but they have like a topological winding number. So they are projected, they are proposed, I mean, for the next generation of ultra-dense magnetic memories, but in particular, they have a topology and that is protected principle from like spinning sites, like it's opposite in the case of magnetic domains or vortices, when they can affect strongly by the pinning sites or the defects in the material. There are different type of skyrmions, maybe two types. Usually people talk about like NIP type skyrmions or block type skyrmions. And then this is due to the fact that they have helicity. For example, another property of these skyrmions, for example, for NIP type skyrmions, so it's like the angle is, we're talking about 0. For block type is like pi/2. Usually, skyrmions in particular form in magnetic system when you have like broken inversion symmetry. So you have like due to spin orbit interaction, which leads to this DMI. So principal DMI, it's you have like kind of change coupling plus multiplied by this DMI constant. And usually you can observe this kind of skyrmions in the system where you have magnetic elements, for example, iron, cobalt, nickel, and high spin orbit coupling. I mean, platinum, iridium, etc. So, for example, here show the image skyrmions of on iron monolayer on iridium, and also palladium iron on iridium mapped like using STM. Usually, skyrmion also counterparts, they have equal helicity but opposite topological charge. I mean, it can be, so this is usually referred as anti-skyrmions. So I refer this very nice review paper written by Alexei Kovalev from UNL. So this skyrmion, these anti-skyrmions in principle can be stabilized by anisotropic DMI, dipolar interaction, and magnetic disorder. So when it comes to the application, so over the last few years, there was huge interest in using this chemical kind of application. I just show you here this very nice demonstration from Alex Hoffman group, where principally you can blow these magnetic skyrmion bubbles with current. In this case, in this TLRC system, the material is cobalt iron boron. And also, usually they are proposed to serve as information carriers on a magnetic racetrack with low current density. The fact that you can write, I mean, switch the state of the skyrmion and then use like normal magnitude transport measurements or to read out the spin state. Also, recently, I mean, just a few years ago, there is like huge interest in using these skyrmions for like normal form computing. The idea there is to use the response, nonlinear response originating from the magnetic field induced dynamics. I mean, if you look here, so you have some input and then you get output, and based on the reservoir, for example, by changing the amplitude of the magnetic field, so you can create increase in number of skyrmions, and then therefore in this paper, they show some examples where you can do this neuromorphic computing, which also is getting a lot of interest recently. Also, there is a very nice proposal in this physics review letter where it was proposed that you can also use this skyrmion as a qubit. In this case, the information is stored in the quantum degree of helicity. So the logical state can be adjusted by electrical magnetic field. So more information can be found in this paper. So far, I mean, I talked about scanmiums, but usually this scanmium exists in systems. For example, it can what's called referred as bulk DMI. This bulk DMI, for example, we have this controsymmetric crystal structure. So this what's called the chiral B20 crystals. Also in certain ferroelectric or certain ferromagnetic spinels. So in general, in this case, you can create this DMI. So usually DMI is kind of weak because it's dominated by the symmetric exchange. And in this case, you can also stabilize these block type scanmiums as demonstrated in many systems. For example, this magnetic scanmium crystal formed in iron germanium system. So these kind of materials usually they lack the tunability and principle disorder, or to create this kind of spin textures, you need to go to low temperatures. So usually this system is very difficult to create DMI in particular at room temperature. So another kind of DMI is called referred as interfacial DMI or DMI. Usually you can engineer by making heterostructure of ferromagnetic heavy metal layers. And then this leads to you break the inversion symmetry. And for example, by choosing the heavy metal, so you can increase this DMI strength. And for example, this DMI is really high. You can reach up to 10% of Heisenberg exchange. And in this case, it's stabilized nil scanmiums. So for the advantage of these systems, I mean, you can observe room temperature scanmiums isolated for example, by increasing the magnetic field or increasing let's say the heavy metal or changing heavy metal, you can go from isolated to the same scanmium lattice. I mean, for example, in this example, you can get this scanmium lattice, which is very interesting in terms of high density memory applications. So for these systems, usually I put this in red, like the growth can be challenging. I mean, also the DMI decreases like rapidly, I mean, from the interface. So if you go to a few nanometer thick ferromagnetic material, then so the DMI gets weaker. That's why you need many layers to increase DMI, and then you choose the heavy metal that has highest spin orbit coupling. So recently, there was like another way to engineer a DMI, and then this is based on continuous gradient of composition. In this case, for example, I show here cobalt platinum, or so by changing the composition of cobalt from the upper surface to the lower surface to the substrate, this is like color map of a color content. So in principle, you induce what's called magnetic asymmetry. And this magnetic asymmetry, in addition to the spin orbit created by the heavy metal in this case, or it can be rare earth as well, so leads to this DMI interaction, so DMI forms. So in principle, in this system, people used BLS. For example, our collaborator used this BLS to measure DMI strengths using BL1 light scattering by looking at the asymmetry between stocks and stock peaks. So one can know the amplitude of the DMI. So the conclusion of this word, without spin orbit coupling, DMI is almost zero. So that's like that's mean DMI is related to this bulk magnetic asymmetry and also as well as spin orbit coupling. The second important thing is principle. This DMI is proportional to the composition gradient. So if you increase, I will define later what composition gradient mean. That means if you increase the content or the composition gradient, for example, we reach 50%, you can get sizable DMI, about 0.16 or millijoule per meter square. Also, DMI usually is uniform through the material. So that's why so this kind of system is getting a lot of attention. And then in addition, this is single layer. So you just by changing somehow the composition while growing the material, you can create this DMI. It's not a case of multi-layer when you need to create layer, another ferromagnet, heavy metal to increase DMI. So I just want to mention also that this, this system in particular for cobalt platinum, usually it has showed that you can induce field-free switching. You can switch the perpendicular magnetization. And then this is believed to come from the composition between gradient-induced damping-like torque and also low crystal symmetry induced M3 torque. So this paper described very well. And also there is another system, is cobalt TB, so where also you can induce switching due to DMI as well, and also bulk magnetic asymmetry. So that makes this system interesting not only for scandium but also for spintronics. So one can combine these properties to study interesting physics phenomena and as well for different kind of applications. So the system we study in particular is so we grew our collaborator from Qingsheng Chen at Singapore National Universities. They grew basically this cobalt platinum. We vary thickness from, in this case, 10, 20, 30 nanometers on STU. Also, we use like SA2 nanometer just to coat the film to prevent from any oxidations. So this is done just using DC or AC magnetometry, magnetosputtering. So in principle, this is done on single crystal substrate. So now, if I want to define exactly what we mean when we say delta, for example, 50%, so this is like, goes back to here, how we define the gradient content. So in this case, like the starting, the ending, for example, can be defined as like here, and then the gradient parameter is just like the content of film, in this case, cobalt, from the upper layer to the lower layer. For example, if in this case we are studying cobalt platinum 3, and we go to cobalt 3 platinum, so in this case, you have the initial content is 25%. You go to the final content 75%. So by doing the delta X is this 50%. So in this talk today in particular, I will only show the results on 10 nanometer thick, and then where we have like both positive and negative. I mean, whether you go from cobalt platinum 3, cobalt 3 platinum, or cobalt 3 platinum to cobalt platinum 3. And then we refer to this gradient composition engineered films as GCOPT. So our colleagues in Singapore did characterization using XRD. So you see well-defined peak. Also, there is some broadening, which confirm you have like a gradient composition in your thin films. So also they measured like the normal polar magnet optical curve loops. And then we find in particular for positive gradient, these films, they have like near perfect square loops, which indicative also of PMA. So this is magnetic perpendicular magnetic anisotropy. So we did also in some squid measurements in plane and out of plane. So we can know that MS still the same for both films, whether it's positive or negative gradients. There's like slight change of anisotropy. I can explain later exactly why you have that little change in anisotropy. So after we know exactly what's the MS, also the effective magnetic anisotropy, we used topological Hall effects. In this case, we have some devices on these films, and then we try to measure the resistance. So usually we do magnetotransport measurement as well, squid measurements. And from here, you can measure the resistance or the, you have like the normal ordinary Hall effects. You get also the anomalous Hall effect, and then you get topological Hall effects. So by subtracting, usually, for example, in this case, the signal from VSM from SQUID. So one can get this topological Hall effect blue signal. So you have like a positive or negative depends on the applied magnetic field. And both this, as I said, measured by, we use the SQUID. And then, so also we did some measurement on the positive sample. I will show you later. So to correlate, to check whether, because usually this topological Hall effect is indicative of the presence of spin textures. So to check that, we used magnetic force microscopy here at UNL. So in here, I show somehow, for example, this point I, 2, 3, 4, 5, just how principle, the farther away from the topological Hall effect peaks, you have like, you see nothing, there's like creation of these isolated spin textures, and then the density start to increase until you form labyrinth structure at zero applied magnetic field, or even, I mean, low magnetic field. And then this is opposite side. So in both cases, you can, in particular, this domain structure here, V usually is a little bit in the negative side, but you can stabilize also skemion at zero magnetic field. So this is like very interesting. So we can create, found like creation of complex spin textures. I mean, like worms, pairs, I will discuss later. Then this correlate as well very well with the Hall effect. So this is done on the negative gradient sample. So we also measure, because this advantage of MFM, you can measure the size or the radius in this case. So we're talking the radius by just cross section, or let's say the positive side or negative side of the loops of the magnetic loop. So one can, using Gaussian 15, we can extract the radius. So usually it varies from 30 to 50 nanometers. So this as expected, you increase magnetic field, you decrease radius of the skemions. And when you go to zero field, because then there is a formation of these multi-domains, and then you go to the labyrinth kind of spin textures. So we did similar measurement on the positive sample. So the positive sample, as I said, from mock measurement, it has high PMA. So in that case, when we do like both VSM and also topological effect, you see that we see that there's very sharp topological effect that it's strong at one side and then it's weak at another side. But when we try to do the measurements, let's say, of these spin textures, one can see, so in around, I mean, it's dominated first by this formation of labyrinth domain structures, but then if you go far away, lower fields, so you can, I mean, basically go this way, and then you can stabilize skemions, and then you saturate, they will disappear. So here again, we plot the radius. Again, of these skemions can vary from 50 nanometers to 200 nanometers. So the fact that this sample has large PMA usually, in particular in the positive gradient side, usually can also lead, so the tip can lead to some kind of artifact. For example, here, if we measure some scan here, so we see like nothing on one of the sides, and you see spin textures. If you just repeat the next scan, usually you can create some spin texture. And then the fact here, because this is like PMA, it has very narrow topological Hall effect region. So while MFM is very good, so it gives information about the size, so it correlates very well to topological Hall effect. So the magnetic tip may affect the spin textures, and then also you cannot know whether this you cannot know the clarity of these spin textures. So that's why we use this NV magnetometry. For those who are not familiar with this technique, so the NV, or nitrogen vacancy, it's defects in diamond. So usually it has 6 electrons, each paired in the ground state or excited state, so that you can get spin triplet for example, in ground state. So you can optically initialize with light, and then you read, it emits light, and then by looking at the emitted light, so you can read out the spin states. Most importantly about this ENVI, the coherence lifetime of these spin states is very long. We're talking milliseconds in the very isotopic pure diamond. And then this can work at wide range of temperature. I mean, from 300 millikelvin until there was a demonstration event 600 Kelvin or higher. So how it works, usually we shine green laser. So this ENVI emits light in this range, 650 to 750 nanometers. And by using confocal microscopy detection, for example, we scan the sample. So you can see here these isolated bright spots. And then this is a single ENVI centers. So the most interesting thing about this defect, they emit single photon light. So if you do the G2 measurement, you see this very well-defined G2 below 0.5, indicative single photon emission. So that's also ENVI applies very well to photonics or quantum photonics applications. So as I said, this is like spin triplet. Now, if you apply magnetic field, so that you split this transition and you get two level systems. And then this is explained by demand splitting. So you get this two-level system, and then principle, if you change the magnetic field, you can measure the magnetic field by looking at because we know this zero field splitting is 287 gigahertz. By measuring the frequency shift, because you apply microwave, whenever you go to the plus minus state, there is a chance to go this metastable state, it's called singlet. It emits less light. So by looking just the intensity of light from here, so you can know the spin state, and then you can measure the magnetic field induced by other objects when it's interacting with ENVI in center. So principle, the Hamiltonian of the system, you have like zero field splitting, and you have like Zeeman term splitting. By engineering the Hamiltonian, so you can use the ENVI for a wide range of applications. So you can use it for mapping, for example, in this case, thermal conductivity, as I worked a few years ago at City College of New York. So by looking the zero field splitting change, so one, you can measure the temperature change in the substrate you are measuring. So in my group as well, so you can engineer this diamond, whether in like nanocrystals, nanopillars, or thin films. So in this case, we have like diamond doped with single ENVIs in contact with a garnet, in this case TMIG. By exciting these spin waves, gold wire, one can see the interference of these spin waves, and then we can measure, basically, the frequency as function of the wave vector. So also in my group, we can map edge states from weakly magnetized samples. So ENVI Center, I mean, it's over the last few years at New Mexico. So we use for NMR spectroscopy by looking at using the nuclear spins, whether like in the diamond or in this case in water. So you can do like very nice spectroscopy. Even you can measure J coupling like in certain molecules with the presented sensitivity and resolution. So in my group as well, we use it to study isolated spin crossover molecules. They have certain memory kind of temperature dependence. Because they are very sensitive, you can measure like micro Tesla fields. And also by looking the T1 relaxation, because this two-level system also, it interacts with the environment. You have like iron in biomolecules, gene spin noise can lead to a decrease, and therefore you can image these biomolecules. So I go to the details how ENVI SPM or ENVI scanning microscopy works. Principle, you have like a diamond a probe with single ENVI. So this we get them commercially. You have the laser here, I mean, focused through a high NA objective. Now do you get some light emitted? And then we collect that light using single photon detectors. And then if you look here, the schematic, so this is, because it depends on the axis, how this ENVI axis can be case 1, 0, 0, that means it's oriented along this angle, around 55 degrees. So now you can, if you apply magnetic field along this direction of the NV axis, so now you can measure the Zeeman splitting by this ODMR, as I showed before. And then this ODMR, in principle, we have microwave antenna to excite this spin state just for readout. And then in here, I show the optical image of single NV in nanopillar. And then in here, I don't show the two peaks, I just one of the ODMR transition of this spin state. So by looking at, for example, by looking at the shift or the shift of these transitions, so one can measure external signal from the spin textures. So that's like how the detection works. So this is like schematic, I mean, this image of the setup that Adam, my students built. So you see like this tiny diamond here, we get from the Skinami attached to quartz. And then this is objective for exciting and correcting the light. And you see also the microwave lobe. So we, in my lab, we use this particular NVSPM to study antiferromagnetic domains. And in this case, I show you, we work with, collaborate with Professor Binek. We study these antiferromagnetic domains in pure boron doped, because this uncompensated surface spins, one can measure supply very nice domains. If you do MFM, you see nothing. So that's like give you how this NV SPCM is very useful to study principle these antiferromagnetic materials. And then we also recently, we can switch magnetic domains at zero applied magnetic field in this boron doped films. So we're working on this as well for another paper. So to go to the materials we are interested on, so usually, as I said, the idea here, as I said, you scan, you bring the magnetic sample here. So by looking, there are two ways to measure. Either you look just the intensity of the fluorescence of these NV centers, and you do optical mapping, or you do quantitative. So you do the full ODMR for each pixel, and by looking at the shifts, whether shift to low frequencies or high frequencies, depends on the orientation of the field, you can get a magnetic image. So, for example, in here, we bring the NV to one of the substrate negative gradient and positive. So now by scanning the tip across the sample, you can see isolated bubbles, for example, for negative, for the positive. Also, you can see isolated bubbles or skemions, certain also worms. And usually this PL is sensitive to quenching. I can explain later why. But usually another way we do the measurements, rather than looking at the change in fluorescence, we just look at the change. I mean, we do full ODMR. So from each pixel, we do this full ODMR, we feed, we get frequency shift. From frequency shift, we can know the stray field generated by these spin textures. That means if it's off here, there is no stray field, but when you cross these skemions or these spin textures, you can see positive or positive or negative, whether red or blue. So now one can zoom. I mean, if you look here, so this is PL, and also this is like ODMR. So these two skemions, it's correct very well. But if you want to zoom exactly on given spin texture, you work at certain standoff. In this case, 200 or 230 nanometers. You can map nicely. You see this like isolated spin texture or skemions with usually blue is like negative, and the red is positive. And the stray field is kind of significant. We're talking 5.6 millitesla, even at 230 nanometers. If you get lower, you can get even to 100 millitesla. So this is works very well. But again, when you use fluorescence quenching, because the fact this spin texture generate high magnetic field, so even if you get NV closer and closer, this skemium, they generate like in-plane field or transverse. The transverse field can lead to mix somehow the excited state and therefore lead to change in the photoluminescence. So in here, we just show the PL image done at different heights. So the one can see that how this PL goes bright, dark, or bright and dark, depends on the standoff from the substrate. So this image, just like by doing repetitive measurement at different standoffs, I mean 250, 200, and get closer. The advantage of this technique that's basically can get closer. I mean, for example, 80 nanometer, we see that the scannium size doesn't change because the farther usually the scannium is big, but when you get closer, you can measure and you can do cross section, and then you can principle know the spin texture or the image very nicely the spin textures. While usually this is not quantitative, that you cannot principle know the amplitude the magnetic field generated, so one can know the special evolution of these spin textures. So I mean, more additional analysis can potentially lead to rapid characterization, because the advantage of this technique is very fast in comparison. In this technique here, you just work at a given applied frequency, so it's just quick, takes few minutes. But while this technique, for each pixel, you need to do full ODMR, and this may take a few hours. So that's why combining this quenching ODMR imaging, then one can map very nicely these skirmits. So in principle, to know exactly what this type of scheme we're mapping, we collaborate with Alexei Kovalev from UNL using micromagnetic simulation. So we provide them all the magnetic properties of the samples. I mean, the MS, magnetic anisotropy, also from the bulk, I mean, from the SQUID VSM measurements, milk. And then they plug it to the model, and then they found that in principle we can stabilize these block kind of skirmions. And in fact, they did, because this is like projection along X and Y and Z. Also, one can measure the projection, or I mean, or the NV, or the stray field created along the NV axis. This is like the calculated and this measured. So if you now try to compare the calculated, the measured one, you see like perfect agreements. So in this case, what we are changing, we're just changing the position of the principle, the NV, to the skirmions, so that we see like very, I mean, this is a lateral cut, but the fact that you have like very overlap, that's principle give you how good NV is good to determine the stray field generated from these isolated spin textures. So while this somehow gives like looking at the orientation of the spins, one can know like this is block type, but we did like Kovalev group in particular did detailed analysis going from the stray field maps, in this case for given skirmium, let's say negative gradient or positive gradient sample. So now, principle they reconstruct the magnetization by using this called inverse propagation protocol. So now, knowing principle the stray field, one can get the magnetization by posing some boundary condition. In the Fourier space. So by doing that, we can, for example, get this like the measured one and then also the fitted. So we can get, for example, for the positive one, perfect agreement as well. You see normalization, we get perfectly normalization. That's mean this kind of a block chirality. For some of the skirmions, we see like distortion along, for example, X or Y, and then this due to the disorder. So that's, I mean, principle correlate very well with MFM measurements. So now, when it comes to, we also observe this pair of skirmion in these kind of materials. So this is like MFM images. I just show only a few, but we did like successive like measurements from across the hysteresis loop. One can see, for example, always there is like pairs, highlighted by stars. So these pairs, for some of them, for example, they stay stable until high fields, until then you saturate the film. Some of them, like you anneal or like cancel one of the pairs. And usually above a certain threshold applied magnetic field, principle, some of the, let's say, whether the pair completely disappear or some of the scandium pair disappears. And then to understand exactly what we are observing, so we mapped, this is again the PL image. So you look at the photoluminescence and then you see, this is one of the examples. We imaged like many pairs. Whether the distance here, we're talking few hundred nanometers to 400 nanometers. So this is like the high resolution image. And this is like PL imaging, but we did also measurement, do this using ODMR, this full quantitative measurement. So you can see in principle the stray field usually generated by this pair. So the fact, for the PL image, the measurement was done at low standoff. That's why you see like very small and isolated. But the NV measurement, because this pair generates significantly strong field, I said up to 100 millitesla, that will lead to quenching, and therefore you cannot do ODMR imaging. So this is like the measured NV image. So Kovalev group tried to make or to model use magnetic simulation, and then surprisingly, so one can stabilize also or scandium anti-scandium pairs. So this is like the magnetic model. In this case, we can stabilize this anti-scandium scam with dipolar magnetic interaction and magnetic disorder. However, so this, while the measurement correlates very well, the NV measurement with the simulation, so it's correlates very well. But Hamilton, Alexei Kovalev did detailed magnetic simulations at higher temperatures, at ambient condition. For example, at zero applied field, you expect to see this like kind of labyrinth structure, some isolated bubbles. If you increase the field to 0.3 kilo Oersted, then you see the formation of this kind of isolate pairs, or isolate like scandiums also as well pairs. And from these simulations, you can see that one can stabilize scandium anti-scandiums. As well, you can, if you have like two pinned scandium pairs. Also, one can stabilize also high winding number scandiums. Here we are just changing the standoff from the NV, like 50 nanometer to 300 nanometers. So, while this our measurement fits very well with this scandium anti-scandium interaction, one need to do inject a current and try to look at the motion of because in principle anti-scandium, they should have different motion than scandiums, and then this is exactly what we are doing now. So just I'm exactly in time to summarize this talk. So we principle, this is the first measurement of topological speed texture stabilized by the GDMI at room temperature. We also confirm the block type helicity. This is expected in bulk DMI materials. The only difference here is a gradient bulk DMI. Also, we found the formation of deep paired scandiums, and we think it's related to the scandium anti-scandium interactions. So in our group now we are having like kind of two projects. One of them is just try to study, as I said, using this scandium Hall effect, or just to know whether one can distinguish whether these anti-scandiums move a different direction than scandiums. So that's one way to prove indeed that this is our anti-scandium or scandiums. And then we have some initial switching measurements. So you can switch the magnetization. So this is a measurement even at zero applied. I mean, zero applied, there is like little effect, but at 100 Ørsted or very weak magnetic field, you can switch the magnetization. And then now we have some initial measurement that when you inject current at a zero field, if you have like a labyrinth domain structure, if you inject current, you can create also high dense of like scanning lattice. So that's one need to do this field-free switching and how you can create these scannions. Also, we are trying to study the effect. As I mentioned, we measured on 20 nanometer, 30 nanometer thick samples. So we try to correlate the strength of DMI to the thickness and also the resulting spin textures. So to summarize, I mean, this work in principle, all the samples, magnitude transport measurement, whole body devices are made by Kihan Chang from Ching Cheng Group at the National University of Singapore. The micromagnetic simulation done, I mean, led by Professor Alexei Kovalev with his postdoc Hamid and the graduate student Edward. But I just want to mention this project is led by my student Adam, who did all NV and MFM measurements with the MFM measurements with that help from Siwan Glu and Suvicha Lamisha. Also, I forgot to mention that Ilya Fisensko from University of Latvia, who helped to reconstruct, help in analyzing the NV data. Also, I have like a last slide. I mean, I'm looking for PhD students, and then thanks, Fan, for advertising my job here in Spintronics online seminar, and thank you very much for your attention.
Thank you very much for the interesting talk. So this talk is open for questions. If you're watching this on Zoom, please just raise your hand. Oh, first, let's thank the speaker. I can start with one quick question. So it seems that with NV center, you can confirm that there is skyrmions or skyrmion anti-skyrmion pairs in the system. But does it correlate with the topological Hall effect that you observe?
Principle,
the bond at zero low field.
Yes. So the measurements we done, all the measurements we done, if you get to just the Hall effect, you're back here. Yes. So if you look here, I mean, so all the measurement done. Yes, because this is a broad region when you see like the signal. So yeah, that's correlate. In fact, if you go above 1,000, I mean, these pairs disappear. So that's like, I mean, I have it here, principle. So that's correlated very well with multiple effects. The fact you stay away from when you have that signal. So I think I have it here. Here, yes. So this is like 100, I mean, it's 1 kilo Ørsted. So the topological effect disappear around like 1.1 kilo Ørsted. Signal like decays.
But just from the image, it looks like the density of skyrmion is not a lot. Is that enough to generate the large topological Hall?
So that's very good question. I mean, as a fact, like because this, so we are measuring, in fact, in our films, we think the DMI is like 0.1 millijoule, but we are collaborating now with Benjamin from the University of Delaware to measure DMI with BLS. So I think it has to do with the strength of DMI, because from these measurements, usually first, like in general, if you have DMI stronger, this gets narrower and sharper and higher. So the intensity here, you look here, is very weak. We're talking 40 nano ohm per centimeter. It's like very weak signal. And the fact you have isolated skyrmions has to do with the DMI strength. I mean, DMI strength, as I said, in our case, this is measured on 6 nanometers. So our film is like 10 nanometer. So we think it's around 0.1 millijoule per meter squared.
Okay, thank you. Do we have any other question from the audience? Okay, Kirill, please go ahead.
Yeah, thank you for your nice talk, Abdelghani. So with these cobalt platinum films, do you know if they are structurally disordered or if there's some ordering, then what is it? Is there some
Yeah,
anisotropy gradient because of that?
that's a very good question. I mean, from I think if I have usually principle from XRD, you can know that this cobalt platinum peaks. I mean, the fact you have like some peak narrow, so that's there is like some order. You just see like broadening at the sites due to this gradient, like gradient change. But I think I have it here. Like we think, in principle, so we did some because like so they were zooming in this peak, but the fact that depends whether you go from cobalt platinum 3 or cobalt platinum 3, you can create different orders, whether, I mean, like this type of order structure, L0, cubic, tetragonal, or hexagonal. So the fact that you create this different order based on whether you go from cobalt platinum to 3 to cobalt platinum 3, so that's fact you can some order, but it will change also magnetic properties. So that you can because for densely packed, let's say system, you get more high PMA, but for FCC less packed. So so that's your question.
Yeah. So the answer is
yes.
there
I
is
mean,
no significant ordering, or
I think
don't.
yeah. I mean the I would say if you look in XRD peaks, you see some orders. I mean, you see like peaks there. If there are no order, then I mean
But this 40 degree to theta, what is it? Which ordering does it correspond to?
I don't have the angle. I mean here, but I mean we see here like you have your cubic, tetragonal, so that's like a composite of different order crystal structures.
Yeah, but those correspond to different concentrations, right? So at 50%, the thermodynamically equilibrium phase is L10. There's also some reports of L11 in thin films, which is surprising. But do you see any specific evidence of these?
Yeah, I mean, so to be honest, like, I mean, we did this principle because, like, we tried to explain why you have, like, I mean, go back here. We try to explain the different change the magnetic anisotropy because, like, certain positive, for example, you see the magnetic anisotropy is weaker. And then our colleagues, they did some detailed XRD. So, I mean, I just showed one of the slides. So I think it's, I cannot exactly answer the question directly, but we think there is mixtures of different or crystal structures. Or I mean, what that changes from whether you go from cobalt platinum 3 or cobalt 3 platinum.
Okay, I see.
But
So
again,
is there some uniaxial anisotropy in any case?
in principle, if you look, I mean, that's a very good question. In principle, for positive gradient, they have like almost, I mean, like PMA, perpendicular magnetic anisotropy. But for this, like, I mean, the negative, the positive, yes. For the negative one, usually they have some kind of, it seems like they have some, whether out of plane magnetic anisotropy, whether it's in initial or that's, I don't know, I need to check, but.
So you have an easy axis.
Yeah, I mean, yeah, for the positive, yeah. I mean, you see perfectly. You have like PMA. And then I didn't show here. I mean, we measured on principal other films, but I can show you here. I mean, I don't have it, should have it here. Principal. So in this case, it's not like a gradient, but whenever you decrease the thickness of the cobalt platinum to 2 nanometers, so in this case, you have like perfect, I mean, like PMA. So in our 10 nanometers, so we found that like the positive gradient, they have this almost like perpendicular magnetic anisotropy, but the negative one, they have like a little bit any actual anisotropy that in fact because you have FCC kind of ordering that's less packed. That's why you have like different magnetic properties. I don't know if I answered your question, but
yeah. Yeah. So for the L10, you can actually expect different ordering domains with different orientations.
yeah. So yeah, I mean, by the way, this is like principle the one need to do further analysis because we are trying to do as well TM because we want need also to correlate like how this is ordered along. I mean, along the films or just portion of the films. Because in earlier studies, they found that there's formation of platelet during these platelets. Maybe
Yeah,
they have
it can be complicated microstructure, I suppose.
It's more complicated. But
the underlying sample is polycrystalline in this case, or is it textured? What do you think?
In this case, I think I mean I need to check. I think it's textured, but it depends on
001 with
I mean, I don't know. Because in this way, the way we explain here, we say like principally you have different. I don't have the peaks here, but I mean, I have another slide when you say exactly the peaks. It usually is not 011. It has some 200. It has some numbers, so some planes.
Okay, thank you.
Great. Do we have any other question? Okay, if there's no burning questions, I don't see any question on YouTube. So I guess we'll just do the live streaming and recording at this moment. And we encourage you to stay and have further discussions